Hello, everyone. Today we'll talk about freezing and gravitation waves from our early universe. My name is Schütte-Engel, and this talk is based on two publications. One together with Andreas Ringrad and Carlos Tamarit, and the other one together with Jacopo Giglieri and Enrico Speranza. So let's get started. Before I say something about gravitation waves, I want to discuss how we think our early universe looked like. You see the highest energy scales, for example, the Planck scale on the left, and if you go to the right, you go to lower energy scales or to later times. We think that there was a phase of inflation, which was followed by a phase of preheating, typically around 10 to the 15, 10 to the 16 GeV. After preheating, our universe was radiation dominated, and there was an electroweak phase transition around 100 GeV, and the QCD phase transition around 0.1 GeV. Also in the radiation-dominated phase, there was an event called Big Bang nucleosynthesis around 1 MeV. After that, after radiation domination, our universe was matter dominated. And in this phase, the CMB was released. Today, we are in a dark energy domination phase. Yeah. And I was showing this sketch here to emphasize that currently on Earth, we only observe directly relics from the CMB and from BBN. We don't really observe directly relics that were produced prior to BBN. However, when we would be able to detect gravitational waves from the early universe, this could change. So gravitational waves from the early universe can teach us a lot about what was going on prior to BBN. So let me now focus on the very early universe. In principle, gravitation waves can be produced in many ways. So one example are gravitation waves from inflation. You can also have gravitation waves from preheating, or to name another example, from first-order phase transitions. However, in this talk, I will talk about gravitation waves that were produced from the thermal plasma. Here, the thermal plasma is depicted by these different colored dots, which should depict different particle species in your plasma. The crucial parameter that we will always talk about is the maximum temperature of the thermal plasma at the start of the radiation dominated phase. Good. So the maximum temperature can be, in inflationary scenarios, the maximum temperature can be at most 10 to the 15, 10 to the 16 GeV. However, in modified cosmological scenarios, this can go up even to the Planck scale. The lower bound of Tmax, in principle, Tmax has to be only slightly above BBN. However, to have successful leptogenesis scenarios, the maximum temperature is often required to be above the electroweak phase transition. So this parameter that we don't know can basically lie slightly below the Planck scale or slightly above the electroweak phase transition. In the last part of the talk, I will tell you how you can determine the maximum temperature from the gravitational wave spectrum that is from the gravitation waves that are produced from the thermal plasma. All right, so let's get started and let's talk about how gravitation waves from the thermal plasma are produced. So in the thermal plasma, you have different particles, and these different particles have typical momenta that are on the order of the temperature. And since they have typical momenta on the order of temperature, they can also collide and produce a graviton. So this is depicted here. So two particles collide and they produce a gravitational wave, and this gravitational wave then gets redshifted to later times. So what really happens is that the particles that collide at Tmax produce a gravitational wave spectrum that peaks at the maximum temperature. And this is then redshifted. So for example, if you redshift this to a later temperature, the spectrum peaks also at T1, at this temperature T1. The crucial part here is, the essential part is, that the gravitational waves which are produced later on at T1 also have a gravitational wave spectrum that peaks at T1. So you get an enhancement effect, so to speak, because the gravitational waves that were produced earlier on due to the redshift temperature relation peak at T1, and the gravitational waves which are produced at T1, they also peak at this other temperature, right? So these two spectra, the peaks of these spectra add up. All right, so this is the crucial thing. And what I just said in words is written down here as a formula. So consider the gravitational waves which are produced earlier on with Kmax. If you redshift them to the frequency today, this is done by this equation. So you have to divide by the maximum temperature, and you have to multiply by these G star functions evaluated at temperature today and at the maximum temperature. So G star basically encodes how many relativistic degrees of freedom are in your plasma. Okay. The crucial thing here is that these G star functions do not change a lot above the electroweak phase transition. And therefore, this is approximately the same when you evaluate the G star functions at T1. And this is the crucial reason why the gravitational waves here and here get roughly redshifted to the same frequency today. Okay, so I already argued that Kmax over Tmax and K1 over T1 is on the order of 1 because the gravitational waves are coming from thermal fluctuations. The G star functions evaluated today and at the temperature T1 or Tmax, when you take the third root, this is also on the order of 1. So the frequency today is basically determined by the temperature today. And when you convert this to a frequency, the temperature today, you end up in the microwave regime, or in other words, in the gigahertz regime. And that's why we dubbed this the cosmic gravitational microwave backgrounds, short CGMB. And in the end of the talk, you will really see that this peaks in the gigahertz in the high frequency regime. So these gravitational waves from the thermal plasma are really guaranteed to be there. And this is another important thing, because we know that at some point our early universe was radiation dominated. And having such a gravitational wave spectrum is a direct consequence of this fact. Okay. And the processes that basically generate the CGMB are typical freeze-in processes. And hence the title of this talk, freeze-in, because these gravitational waves are produced out of equilibrium from the thermal plasma. And this is in close analogy with, for example, dark matter production processes, which are also produced from a thermal plasma. And this is then called dark matter freeze-in production. Yeah. So, okay, good. So this was basically the introduction to this talk. What I'm going to do now is I will tell you in detail how you can calculate the gravitational wave spectrum. And I will first do this for a toy model where you have in the thermal plasma only a complex scalar with a quartic coupling. And then after I explained how you can calculate the gravitational wave spectrum in this toy model, I will go on and tell you how you can do this for the standard model or even beyond the standard model theories. All right, so let's start with the complex scalar model. To calculate the gravitational wave spectrum, you need two distribution functions. So one for the scalars and one for the gravitons. And these distribution functions fulfill evolution equations. So for example, you have here the rate of change for the graviton distribution function. It has a gain term and it has a loss term, and similar for the phi distribution function. Because we're interested in gravitational waves, let's focus on the graviton distribution function. So the gain term here in orange and here in orange is basically you have to sum over all processes which have at least one graviton in the final state, because you want to produce gravitons. Yeah. And then you have to integrate over the phase space. For the process that you consider, you have to compute the matrix element squared, and then you have to weight everything correspondingly with distribution functions. So one very general process is written down here. So you have some incoming gravitons, outgoing gravitons, incoming phis, outgoing phis, and so on. All right. So if you look at these equations, you see that this is very difficult to solve, simply because you have derivatives here and you have basically these functions that you want to determine under this integral. So, and on top of this, these two equations are coupled. So it's very difficult to solve this. However, what we can do in our case, we can obtain a perturbative solution. So the perturbative solution works as follows. We say that the zeroth order solution is basically that the gravitons, like the graviton distribution function is a Bose-Einstein distribution function, which basically means that this is in thermal equilibrium. And the graviton distribution function, the zeroth order is 0, because you will produce very few gravitons. Okay. And when you do the math, you see that the graviton distribution function has two lowest order contributions. So this depicted here as FH22 and FH04. I will explain this naming convention in a second. So this FH22, which is depicted in blue, is coming from processes which have just a single graviton in the final state. So as an example, you see here this process, you see a single graviton, you see the quartic coupling here, and yeah, the matrix element squared is proportional to lambda squared, which is the quartic coupling here, so the coupling in the heat bars, and 1 over m Planck squared. And if you wonder, so this is actually not a dimensionless parameter. So the dimensionless parameter is actually the maximum temperature over m Planck squared. Okay. Now you can also understand the naming convention here. So the 2 comes from the lambda, and this 2 here comes from the Tmax over m Planck. Okay, so because, as I said, you have 2 expansion parameters. One is the coupling in the heat bus, and one is Tmax over m Planck. All right, this is the first lowest order contribution. The second lowest order contribution is coming from graviton pair production processes. And here you see some examples. The matrix element squared in this scenario is proportional to Tmax over m Planck to the power of 4. And hence we call this FH04 because you have 0 powers of lambda and 4 powers of Tmax over m Planck. All right, so these are the 2 lowest order contributions. And you will see in a second that because these here are proportional to Tmax over m Planck, and these are proportional to lambda squared over Tmax over m Planck squared, that of course, graviton pair production processes are dominating when the maximum temperature is high enough, and single graviton production processes are dominating when the coupling in the heat bars is large enough. Okay, right. Before I will tell you something about that, let's move on and briefly discuss higher order effect. This is work in progress. You can get interference effects, for example. And then you have these quantum gravity effects, and I mean like virtual gravitons, and they give you matrix element squares on the order of lambda squared Tmax over m Planck to the power of 4, which is in total on the order of 6. This is a small correction to the lowest order diagrams that I've discussed before. And yeah, so we are calculating this, and yeah, stay tuned. But yeah. The message is that quantum gravity effects will show up as small corrections in the gravitational wave spectrum. Okay, so here's actually the gravitational wave spectrum. So I'm showing this omega GW. This is basically the energy density per logarithmic frequency interval. And it has 2 contributions, lowest order contributions, from graviton pair production in blue and from single graviton productions in red. These psi functions here and here, you obtain them by calculating the matrix element squareds and performing the phase-space integrals. However, the important part here is that this is proportional to lambda squared, and this part is proportional to Tmax over m Planck squared. So what I just said before, you can see this here explicitly. For sufficiently high temperatures, graviton pair production processes dominate, and for sufficiently large lambdas or sufficiently low maximum temperatures, single graviton production processes dominate. Here's an example. Here we plot the spectrum against the frequency. Again, this peaks at very high frequencies, so around 10 to the 11 hertz. And in this scenario, we choose a maximum temperature in units of m Planck of 10 to the minus 3 and a coupling 10 to the minus 1. In this scenario, graviton pair production processes are way smaller than single graviton production processes, And the total spectrum, which is shown in black, is basically completely dominated by single graviton production processes. When you increase the maximum temperature by 1 order of magnitude, you see that now graviton pair production processes can dominate. And the total spectrum in black gets this unique shape, so gets the kink here, because these two contributions, because of the two contributions. If you increase the maximum temperature even more, you see that you can even saturate the bound that's coming from dark radiation. Yeah. So this tells you that this is a powerful method to constrain the maximum temperature of our early universe. So, but yeah, keep in mind that this is still a toy model here. Yeah. So it's not a realistic model. All right, let's go on and discuss what happens in the standard model, for example. The calculation is pretty much the same. You still get the scaling, that this is scaling with the coupling in the heat bars, and this is scaling like Tmax over m Planck squared. The only thing that changes is that you have to calculate way more diagrams. It's way more technical. So this was done in the standard model for single graviton production processes by Giglieri, Jackson, Leine, and Zhu in 2020. And the results are here. So you see that this basically, the spectrum here for different maximum temperatures, you get the largest value of omega GW for the largest temperature. And the lower the temperature, the lower the maximum of the spectrum. And this is simply because the higher the maximum temperature, the longer you produce these gravitational waves, and hence the more gravitational waves you get in the end on Earth. Okay, so this is in the standard model, and because this is only done for single graviton production processes, you see that the spectrum scales linearly with the maximum temperature. Okay, so what happens in beyond the standard model theories? So if you remember from the beginning of the talk, and this is what you what you get in the end, that the peak frequency here, the peak frequency scales like 1 over G star evaluated at the maximum temperature, and then you take the third root. And this is very, very important because, for example, in the standard model, G star at the maximum temperature is 106. However, in the minimal supersymmetric standard model, it's 228. So you would expect, if you have the minimal supersymmetric standard model at these ultra high temperatures or energies, then you expect the peak to be at a lower frequency. So you can use this to constrain or to constrain particle physics models at ultra high temperatures.